When we think about space, we usually imagine a vast emptiness filled with familiar features like stars, planets, and galaxies. Features that feel distant, but ultimately understandable. The universe feels predictable and structured, where everything follows the laws of physics. Every motion can be calculated, every object can be classified, and every event can be traced back to its cause. But the reality is not always that clean. Because once in a while, something happens that doesn't quite fit into that picture. An event that doesn't just seem unusual, but actively challenges the understanding of space that we have built over centuries of observation. Today, we are going to look at 5 such events. These are not myths or internet stories. They are recorded events and documented anomalies that were studied carefully and, in many cases, left unresolved because no clear answer was ever found. On August 15, 1977, at the Big Ear Radio Telescope operated by Ohio State University as part of Search for Extraterrestrial Intelligence, or SETI, astronomers were conducting a long-running search for extraterrestrial signals, scanning the sky for anything that might stand out from the natural background noise of the universe. The system generated long streams of numerical data, representing the intensity of radio signals detected at specific frequencies over time. When astronomer Jerry R. Emmon reviewed one of these printouts, he noticed a sequence that immediately stood apart from everything else on the page. The sequence was 6EQUJ5. This was not a random string, but a coded representation of signal strength, where each character corresponded to a level of intensity, and in this case, the signal rose sharply to a peak and then declined in a smooth, symmetrical pattern. That pattern mattered because it matched exactly what scientists would expect from a fixed source in space passing through the telescope's field of view as the Earth rotated, meaning that whatever produced the signal was not local interference, but from something fixed far out in space. Emmon circled the sequence and wrote a single word in the margin: "Wow." What made the wow signal different from ordinary radio noise was not just its strength, but its structure. Most natural radio emissions, such as those from stars or galaxies, tend to be broad and diffuse, spreading across a range of frequencies. The wow signal, however, was narrow-band, concentrated within a very specific frequency range, around 1,420 megahertz, which is also known as the hydrogen line, a frequency naturally emitted by neutral hydrogen atoms and considered significant because hydrogen is the most abundant element in the universe. This frequency is also part of a protected spectrum, a frequency range reserved for astronomical research, in which Earth-based transmissions are forbidden. In addition to being narrow-band, the signal was also unusually strong, far above the background noise, yet it did not show any of the characteristics typically associated with human-made transmissions, such as modulation patterns or repeated bursts. It appeared once, maintained a smooth rise and fall consistent with a distant source, and then vanished. At the time of the observation, the Big Ear Radio Telescope relied on the rotation of the Earth to scan across the sky. Given the speed of Earth's rotation and the spatial width of the telescope's observation window, the Big Ear could observe any given point for just 72 seconds. A continuous extraterrestrial signal, therefore, would be expected to register for exactly 72 seconds. and the recorded intensity of such a signal would display a gradual increase for the first 36 seconds, peaking at the center of the observation window, and then a gradual decrease as the telescope moved away from it. The duration of the WOW signal was exactly 72 seconds. This confirmed that the signal was not something moving quickly through space, but something relatively fixed in position. Whatever it was located in the direction of the constellation Sagittarius, where the closest easily visible star is Tau Sagittarii. In 2022, a paper published in the International Journey of Astrobiology identified 3 likely Sun-like stars within these coordinates. One of these stars is 2MASS 19281982-26400123, which is located 1,800 light-years away. This is approximately 132 light-years away from the estimation of where the closest civilization to Earth is most likely to exist, as calculated by the Italian SETI astronomer, space scientist, and mathematician Claudio Maccone. Following the initial detection, astronomers attempted to locate the exact origin of the signal, focusing on 2 possible regions of the sky where it could have originated, based on the design of the telescope. Multiple follow-up observations were conducted over the years, including more targeted searches using other radio telescopes, but none of these efforts succeeded in detecting the signal again. This lack of repetition is one of the most frustrating aspects of the WOW signal, because without a second observation, it becomes extremely difficult to confirm its origin or rule out alternative explanations with certainty. As a result, the WOW signal exists in a space between explanation and uncertainty, where no single theory fully accounts for all of its observed characteristics. Until date, its source remains unknown. There are certain discoveries in astronomy that do not immediately feel dramatic, because they are not explosions or collisions in the sky, but rather subtle irregularities hidden inside data. Patterns that only become visible after long observation and comparison with everything we think we understand. Tabby's star is one of those discoveries, a distant star that does not behave the way a normal star should, and whose behavior has forced astronomers to consider explanations ranging from unusual natural causes to ideas that are the stuff of science fiction. Tabby's star, also known as WTF star, was first observed as early as the year 1890, but it was extensively studied from 2009 to 2013 by the Kepler Space Telescope as part of its mission to detect planets. The telescope detects tiny dips in the brightness of stars as planets pass in front of them. When planets orbit in regular paths around the star creates predictable and repeating patterns of dimming that can be identified and analyzed. But when researchers examined the data for Tabby's star, they found something very different. Instead of small periodic dips, the star's brightness dropped in large, irregular, and unpredictable ways, with some dips blocking as much as 22% of the star's light, a level far too large to be caused by a typical planet. The first major dip, on the 5th of March 2011, reduced the star's brightness by up to 15%, and the next 726 days later by up to 22%. A third dimming around 8% occurred 48 days later. In comparison, a planet the size of Jupiter would only obscure a star of this size by 1%, indicating that whatever is blocking light during the star's major dips is not a planet, but rather something covering up to half the width of the star. More importantly, these dips did not follow a consistent pattern, which meant that they could not be easily explained by any known orbital system. The scale of the dimming suggests that something enormous was passing in front of the star, yet the lack of regularity suggested that whatever was causing it was not a single object in a stable orbit. In 2017, by the end of a 3-day dimming event, the astronomical community was described as having gone mildly bananas over the opportunity to collect data in real time on the unique star. Astronomers globally dropped their own projects to provide telescope time and resources for Tabby's star. The independent SETI projects, Breakthrough Listen and Near-Infrared Optical SETI, both at Lick Observatory, continued to monitor the star. Over the years, a few hypotheses have been proposed to explain the dips in brightness, such as solar and cosmic material orbiting the star, although none of these fully fit the observed data. They provide a part of the solution, but fail to deliver on the full explanation. As the data continued to be analyzed, one idea began to circulate, not as a conclusion, but as a possibility that could not be immediately ruled out. It was the presence of an artificial structure, something massive and complex, possibly designed to capture energy from the star. This idea, often referred to as a Dyson swarm, is a concept in which an advanced civilization surrounds a star with structures to harness its energy. The idea was originally proposed by physicist Freeman Dyson, who suggested that a sufficiently advanced civilization might outgrow the energy available on its home planet and begin harnessing the full output of its star. Instead of a single solid shell, which would be structurally impractical, a Dyson swarm could consist of countless individual satellites, collectors or habitats orbiting the star in coordinated paths, forming a loose distributed network. From a distance, such a structure would not appear as a clean, uniform object, but as an irregular and constantly shifting pattern, with different parts blocking different amounts of light at different times. And that detail is what made the idea briefly relevant, because the light from Tabby's star did not dim in a smooth or repeating pattern, but in deep, uneven, and unpredictable drops. The kind of pattern that, at least in theory, could be produced by a large number of independent objects moving without perfect synchronization. Over time, further observations provided more data, allowing scientists to refine their understanding of the system. The leading explanation today involves clouds of fine dust, which can produce irregular and wavelength-dependent dimming, meaning that different colors of light are blocked to different degrees. This aligns with some of the observed behavior and provides a more natural explanation for the phenomenon. However, even this explanation is not entirely complete. The source of the dust, its distribution, and the reason for its unusual behavior are still not fully understood, and the system does not perfectly match other known examples. And so, the mystery of Tabby's star remains, waiting for an explanation that may not come anytime soon. In October 2017, astronomers using the Pan-STARRS system detected a faint object moving rapidly across the sky. At first, it appeared to be another asteroid or comet, one of many small bodies that pass through the solar system. But when its trajectory was calculated, something immediately stood out. The path was hyperbolic, which meant that it was not bound to the sun by gravity and had not originated within our solar system. It was coming from outside. It was named Oumuamua, which is Hawaiian for scout, and reflects the way the object was like a scout or messenger sent from the distant past to reach out to humanity. It roughly translates to first distant messenger. Oumuamua was the first known interstellar object ever observed passing through our system, a visitor from another star system that had likely been traveling through space for millions or even billions of years. As astronomers gathered more data, they began analyzing how the object reflected light, which allowed them to infer its shape. The results suggested that Oumuamua was extremely elongated, possibly several times longer than it was wide, unlike most asteroids, which tend to be more compact or irregular in shape. Later studies proposed that it might instead be a flattened disc-like object, similar to a pancake, which would also produce the observed variations in brightness as it rotated. Either way, the object did not resemble the typical shapes seen in known comets or asteroids, adding to the sense that it was something unusual. The most puzzling aspect of Oumuamua was not its origin or shape, but its motion. As it passed close to the sun and began moving away, it exhibited non-gravitational acceleration, meaning it was being powered by something else than gravity. In comets, this kind of acceleration is usually caused by outgassing. the release of gas as ice heats up, which creates a visible tail. But Oumuamua showed no clear signs of outgassing. There was no visible tail and no direct evidence of material being ejected. This created a problem, because the acceleration suggested that something was pushing the object, like a propulsion engine, but there was no obvious mechanism to account for it. Scientists proposed several hypotheses to explain this behavior. One idea was that Oumuamua might be composed of unusual materials, such as hydrogen ice or nitrogen ice, which could turn directly from solid to gas without producing a visible tail. Another possibility was that the object's shape allowed solar radiation pressure, the force exerted by sunlight, to push it slightly, especially if it were thin and flat. This led to a more controversial suggestion that Oumuamua could be a form of artificial object, such as a light sail designed to harness radiation pressure for propulsion. Most scientists consider natural explanations more likely, but none of the proposed models fully explain every observed feature without requiring specific and somewhat unusual conditions. One of the most frustrating aspects of studying Oumuamua is how little time we had to observe it. It was detected on the 19th of October 2017, approximately 40 days after it had already passed its closest point to the Sun. When it was first observed, it was about 33 million kilometers from Earth, about 85 times as far away as the Moon, and already heading away from the Sun. By the time it was detected and identified as an interstellar object, it was already on its way out of the solar system, moving too quickly to be followed in detail for long. This meant that astronomers had only a limited window to collect data, and once that window closed, the object was effectively lost. We cannot observe it again, unless we send a probe that can catch up with it and return detailed observations. Till then, we're left only with the data we managed to capture during its brief visit. Oumuamua is not just important because it was the first interstellar object we observed, but because it did not behave in a way that fits cleanly into our existing categories. It showed characteristics of comets, but without visible outgassing. It had a shape that does not match typical asteroids. It exhibited acceleration without a fully confirmed cause. Each of these features can be explained individually, but no single explanation accounts for all of them at once without introducing new assumptions. In the end, Oumuamua did not leave behind answers. It left behind questions, and it carried those questions with it as it disappeared back into interstellar space. There is a large-scale movement of galaxies in our universe that appears to be directed towards something we cannot observe, something that lies beyond the visible edge of the universe. This is known as dark flow. To understand why dark flow is unsettling, let's first understand what we expect the universe to do. On the largest scales, the universe is expanding, with galaxies moving away from each other as space itself stretches, a process that has been observed and confirmed through multiple lines of evidence. Within this expansion, local gravitational effects can cause galaxies to move toward each other, forming clusters and superclusters. But beyond these local interactions, the overall motion should appear random and evenly distributed when viewed across sufficiently large distances. In other words, there should be no preferred direction, no large-scale drift pulling everything one way. But this understanding of how our universe functions was challenged in the early 2000s, when a team of researchers led by Alexander Kashlinsky began analyzing data from WMAP, focusing on the cosmic microwave background, or the faint afterglow of the Big Bang, that fills the universe. By studying how galaxy clusters interact with this background radiation, scientists can measure the motion of these clusters relative to the rest of the universe. What they found was unexpected. Instead of moving randomly, a large number of galaxy clusters appeared to be drifting in the same direction, as if they were being pulled toward a common point. They found evidence of a surprisingly coherent 600 to 1,000 km per second flow of clusters toward a 20-degree patch of sky between the constellations of Centaurus and Vela. This motion extended across vast distances, far beyond the scale at which local gravitational interactions could explain it. The regions involved in dark flow are not small. They span hundreds of millions of light years, encompassing entire clusters of galaxies, each containing thousands of individual galaxies. The idea that such massive structures could be moving together in a coherent direction suggests the presence of an influence far larger than anything we can directly observe. And that is where the problem begins, because when scientists looked in the direction of this motion, they did not find any visible structure large enough to account for it. There was no massive supercluster, no obvious gravitational source, nothing within the observable universe that could explain why these galaxy clusters were moving the way they were. One of the most intriguing interpretations of dark flow is that the cause may lie beyond the observable universe, in regions of space that are too distant for their light to have reached us since the beginning of the universe. This idea is difficult to test directly, because, by definition, anything beyond the observable universe cannot be observed. We can only infer its existence through its effects. There is also a possibility that this could be the effect of a sibling universe, or a region of spacetime fundamentally different from the observable universe. Alexander Koshlinsky, after analyzing data on more than 1,000 galaxy clusters, claims these measurements show the universe's steady flow is clearly not a statistical fluke. Koshlinsky said, "At this point, we don't have enough information to see what it is, or to constrain it. We can only say with certainty that somewhere very far away, the world is very different than what we see locally. Whether it's another universe or a different fabric of spacetime, we don't know." And so dark flow remains, a question without a clear answer, suggesting that something beyond the edge of our observable universe may still be influencing everything within it. There are signals in space that behave exactly the way we expect them to, and then there are signals that appear once, for a brief moment, and leave behind more questions than answers, like the fast radio bursts. A fast radio burst, or an FRB, is a transient radio wave of duration ranging from a fraction of a millisecond to a couple of seconds, caused by a high-energy astrophysical process that is not yet understood. They do not follow a predictable pattern. They do not last long enough to be easily studied, and yet they carry an amount of energy that suggests something extremely powerful is producing them. What makes them difficult to ignore is not just their intensity, but the fact that they come from far beyond our galaxy, traveling across vast distances before reaching our instruments, which means that whatever is creating them is not only energetic, but also widespread across the universe. And even though we have detected many of these bursts over the years, there is still no single explanation that fully accounts for their behavior, which is what makes them one of the most persistent and intriguing mysteries in modern astronomy. The first known FBR was identified in 2007, when astronomers reviewing archived data from the park's observatory noticed a sudden spike in radio intensity that stood out sharply from the background. At first, it appeared to be a possible error or interference, something produced by the instrument itself or by human activity. But when the signal was analyzed in detail, it revealed a characteristic pattern known as dispersion, where different frequencies of the signal arrive at slightly different times. This effect occurs when radio waves travel through plasma in space, and the amount of delay can be used to estimate how far the signal has traveled. In this case, the dispersion suggested an origin far beyond our galaxy. This meant the signal had traveled across intergalactic space. What made this discovery difficult to ignore was not just the distance, but the intensity. Despite lasting only a few milliseconds, the burst released an enormous amount of energy, equivalent to what our sun emits over several days. This raised an immediate question: what kind of process would produce that much energy in such a short time from such a distant location. There were known cosmic events capable of releasing large amounts of energy, such as supernovae or neutron star collisions, but those events tend to produce lasting signals across multiple wavelengths, not a brief and isolated burst of radio waves. FRBs did not fit neatly into any of these categories. For several years, astronomers assumed that fast radio bursts were one-time events, possibly caused by catastrophic processes that destroyed their source. This assumption seemed reasonable, because if something produces that much energy, it is likely to be a violent and terminal event. But this assumption changed in 2016, when astronomers observed a source known as FRB 121102, producing multiple bursts from the same location. This was the first confirmed repeating FRB, and it created a new problem, because if the source repeats, then it survives. Whatever is producing these bursts is not being destroyed. The discovery of repeating FRBs shifted attention toward objects that could release large amounts of energy repeatedly without being destroyed. One of the leading candidates is the magnetar, a type of neutron star with an extremely strong magnetic field. Magnetars are known to produce powerful bursts of radiation through processes such as starquakes or magnetic reconnection, where the magnetic field suddenly reconfigures and releases energy. In fact, in 2020, a burst detected within our own galaxy was linked to a known magnetar, providing strong evidence that at least some FRBs can originate from these objects. However, this did not solve the entire problem, because not all FRBs behave the same way. Some FRBs repeat, others are detected only once. Some show patterns or clusters of activity. Others appear completely random. Some originate from regions of active star formation. Others come from older, quieter galaxies. This diversity suggests that there may not be a single explanation that applies to all FRBs, but rather multiple processes that can produce similar signals. And even within the magnetar explanation, the exact mechanism that generates such intense and focused bursts of radio energy is still not fully known. Fast radio bursts are not mysterious because we know nothing about them. They are mysterious because we know just enough to realize that there is so much that we do not know. Each of these 5 events are partially understood, and the unanswered parts are set aside as something we will figure out later. The universe is far more complex, more layered, and more difficult to fully understand than we often assume. And the problem is not what we don't know, it's what we think we understand, but don't.